Hi folks, so I recently put together a temperature pressure data logger for some friends monitoring wetland conditions in southern Arizona. For the deployment, I selected an Adafruit datalogger coupled with a BMP280, but it left me wondering what other hardware combinations might have worked and how might their programming and performance differ, and what are the costs and benefits of each approach. While investigating alternatives, I quickly learned that outside of power, there are three important aspects to any data logger used for monitoring ambient environmental conditions. First, of course, you'll need a microcontroller such as an Arduino Uno or a Feather 32U4. Second, you'll need a data logger ranging from a generic Arduino data logging shield to a Feather datalogger. As a side note, all the data loggers I've considered write data to a camera SD card. Third, you'll likely want to timestamp your data. If you use a battery-powered real-time clock, or RTC, time will be saved if or when your Arduino resets due to a power failure. Commercial options for these components sometimes combine features onto one board, such as the Arduino data logging shield, which combines both the data logger with an RTC, but needs an Arduino Uno to drive the same. Or the Feather MO datalogger that combines both a microcontroller with a data logger, but needs an RTC added for timekeeping in the event of power failures. Or how about an datalogger Featherwing, which is another variant of a data logger that includes an RTC but needs to be driven by a microcontroller. And finally, you'll have a variety of sensors to choose from, each having its own ambient monitoring capabilities, accuracy, and precision constraints. In this video, I'll go over programming, tests, and results of 5 different hardware combinations, ranging from an Arduino Uno coupled with an Arduino datalogger shield with a BME280 sensor, to a Feather 32U4 driving an datalogger Featherwing with a DHT22 sensor. The hardware selected is based on what I happen to have in my drawers rather than preference for any particular platform, but it provides a nice foundation for studying data logging in general. First, let's summarize the hardware combinations in a little more detail and programming considerations for each platform. We'll start with an Arduino Uno coupled with an Arduino datalogger shield that has an embedded DS1307 RTC. This, as well as all our other combinations, will include a reference to the wire.h library to facilitate I2C communication with an RTC and our sensors. We'll also include reference to the RTC.h library, which allows us to create time tracking objects for reference in code. All the data loggers I tested communicate using SPI, and thus always reference the SPI and SD.h library. And because we're using SPI, we need to define a chip select or CS pin, as is done here, set to 4 for this particular hardware combination. CS pins may vary by microcontroller and data logging shield, so care needs to be taken when selecting the same, or the microcontroller won't be able to communicate with its data logger. Needless to say, we'll need to include reference to libraries for our sensors. In this case, this is what's suggested by Adafruit for use with its BME280 breakout board for measuring temperature, humidity, and pressure. And finally, all the sketches I'm sharing include reference to a VBAT pin, which, when attached to a voltage divider circuit, can help us read battery voltage for remotely deployed units. Adafruit is kind enough to include a voltage divider on its Feather boards, but in the case of the Arduino Uno, I leave this undefined. And here's the setup for a Feather MO datalogger that's driving a DHT22, which communicates over I2C, as well as a PFC8523 real-time clock, which also communicates over I2C. And here's the setup for a Feather 32U4 datalogger talking to a BMP280 as well as a PFC8523 RTC. And here we have a Feather 32U4 datalogger coupled with a DS3231 Featherwing RTC and a BMP390. And finally, a Feather 32U4 coupled with a Featherwing datalogger that has an embedded PFC8523 talking to a DHT22. Respective libraries and programming details are captured in these 5 sketches developed for all 5 configurations. These sketches were uploaded and tested in these 5 hardware combinations, which log temperature, pressure, and/or humidity for 30 days, each at a 1-minute interval. These were placed on a table under a covered patio in my backyard during the summer monsoon where I live here in Tucson, Arizona. Before I go over the results of the test, I'll quickly summarize the major components of each sketch, all of which are quite similar to one another except for reference libraries, voltage divider pins, and CS definitions. To explain all 5 sketches, I'll use the sketch associated with the data logger deployment at a wetland here in southern Arizona, specifically the 32UF datalogger coupled with a PFC8523 real-time clock and a BMP280. As a side note, all combinations are basically programmed the same way and follow a similar wiring template with the sensor and RTC connected via the I2C, SDL, and SCA pins on the microcontroller. So here you can see the libraries that are created for this particular combination. I've got my library specific to the BMP280 sensor right there, and I've used that to basically create some sensor objects for capturing environmental data. I've got my VBAT pin, which on the feather boards will help me monitor battery voltage and record the same to my SD card. That's all stored in this variable right here, this measured VBAT variable that's set to 0 when I initially start. I've got a myFile object, which is basically what's going to allow me to write data to that SD card. I've got a delay time variable that is basically set to 1 second here, or 60,000 milliseconds. And of course, I've also got an RTC object right here, which is going to help me log time, even in the event of a power failure. Okay, and a little further down in my code, you'll see that I have this card write header function. And what that does is it basically writes a header line to the data file that's being written to by the data logger. So the header file will have something like header column titles like date, time, temperature, pressure, etc. And this is actually quite helpful for determining if you've had a power failure, because if for whatever reason the Arduino resets, it's going to call this line again when it restarts, and you'll see a new header written in your comma delimited file, and you'll be able to use that as an indicator that something happened. Moving on, the first time that you upload this sketch, you're going to want to make sure that you uncomment this line right here. And what that will do is set the time on the real-time clock to the time that the sketch was compiled. Once you've done that, you're going to want to comment this line out again. So just basically add 2 little slash marks right there, re-upload just to make sure that the time on the RTC is set correctly. And then finally, you'll notice that for the PCF8523 in particular, is going to have all these parameters that you can change with respect to drift, deviation, etc. And the reason these are included is it gives you an opportunity to fine-tune that clock. What I've learned about the PCF8523 is that vibration, which is used for timekeeping, can change as a function of temperature and can cause the clock to run a little fast or a little slow. So these are parameters that you can modify if in fact your RTC isn't keeping time properly. Okay, next in my loop function, you can see here that I have a check time function that echoes time to the serial terminal if I have a serial terminal open. Measure values measures the battery voltage off that VBAT pin, and also takes sensor readings. Those values are going to be echoed to the serial terminal via this little function right here. And then I actually write the data via this card write function. And then I'll delay for whatever my delay time is set. In the case of my test, it was set to 60,000 milliseconds, which is basically 1 minute. So this will pause for 1 minute and then just do this process all over again. And when you're done with your data logging, you're going to go ahead and you're going to take the SD card out of your data logger, plug it into your computer, and you'll find a comma delimited file that you can open up in a text editor. It looks a lot like this. You'll have your header right here, and then all your data. collected by the data logger coupled with its sensor on a 1-minute interval. What I went ahead and did was import all of those as individual worksheets into an Excel workbook, and then I combined all the data logs into basically one massive worksheet. This worksheet contains like 230,000 plus records, and I have the loggers and associated sketches identified as 1, 2, 3, 4, 5, as I've done in this presentation. After combining all these into one worksheet, I went ahead and analyzed the worksheet using pivot tables. And just briefly, before I show you the pivot table, I just want to mention that data logger number 3 did reset once 14 days into the test. I'm not sure as to why it reset, but it doesn't look like anything was really lost. It looks like it just reset briefly for 1 minute. Everything was plugged in with wall warts, so I don't know, maybe my tortoise came by and touched something. But the bottom line is that no data was really lost. You can see that the difference when that new header was written was about a minute, so not exactly clear what happened, but I thought I'd just mention that briefly before going into the analysis. So here are the pivot table results for all 230,000 records collected by all 5 data loggers. And basically you can see here very quickly what each one of the sensors, for instance here BME280, DHT22, BMP280, what each one collected by looking at the data that's actually recorded for each row. So in the case of, say, this BMP280, there's no data for average and standard deviation of humidity because that's not a parameter that's collected by that particular sensor. So that explains the gaps in the data that you might see in this table. You can see that I've got 2 tables here. The first one is a pivot table on averages for temperature, humidity, pressure, and altitude, which is something that one of the libraries calculates. And then in addition, I also went ahead and I looked at the mins and the max to see if there were any outliers in the data for all 230,000 plus records. And here you can see that the only parameter that actually showed some real difference between all the sensors was specifically humidity. You look at the DHT22, the second data logger that was collecting data. You can see here that my min of humidity was 17.4%, which was different from this DHT22 and this BME280, which actually did match one another, and that showed up in the averages as well. So that's kind of interesting. And similarly, for all those records, you can see that the BME280 had a max of humidity of 84.2%, which is different from the max humidity that was recorded by the DHT22s, this one and that one right there. So interesting results there. So I was kind of interested in why there was a difference in average high humidity between these 2 sensors. So I went ahead and I looked at the specs sheet. This one right here says that it's good for 0 to 100% humidity readings with a 2 to 5% accuracy. So here I've actually got a range that's specified in the specifications. On this one, there's no range specified. I'm only given basically the accuracy tolerance for this one. So maybe the range on for the high end of humidity on the BME280 is just different. Maybe it just can't read close to 100%. I can't tell from the spec sheet, so I'm just speculating here, trying to understand why I might have gotten a different high humidity reading off the BME280. So you'll also notice that a couple of the libraries associated specifically with the BME280 as well as the BMP390, that there's a function that returns elevation as a function of your barometric pressure. And that's great. That would be great to understand, what my elevation is at a given location. But over the course of 30 days, look at the range that I got in my calculated elevation for both these sensors, which made me question if, in fact, the elevation that's being reported by the sensor really makes sense if I'm getting a range over 30 days. That's the average for my elevation, and then I've got a standard deviation of about 20 meters, so that's pretty significant. So I was curious about this, so I went ahead and I took a look at the code, and you can see here that, that the code mentions a sea level pressure underscore HPA of 1013.25, and this is the assumed atmospheric pressure at sea level, which is used for calculating your elevation where you're measuring barometric pressure. And that constant is forwarded to this function right here associated with the BME library, or this BME object. So let's go ahead and take a look in the library what that function does. And here it is. You can see that what this is going to do is it's going to basically return an elevation value based on this equation right here. Well, where did this come from? So Adafruit mentions that they obtained that equation from page 16 of the Bosch documentation for that sensor. And here it is. And you can see how altitude is going to change as a function of barometric pressure at an assumed 1013.25 HPA, or pressure at sea level. So the thing about this is, as pressure at your location changes over time, the calculated elevation is also going to change because you're relying on an assumed pressure at sea level. So here you can see that the equation in the library comes right off of that data sheet. And here's the atmospheric pressure that's being measured in my backyard over P naught, which is basically the atmospheric pressure at sea level. And in our case, we're just defining that as a constant, right? So by assuming it's constant, what's happening is, as atmospheric pressure changes at our location, is causing a variation in our calculated elevation at our location. So having discovered this and wondering, if I'm right about my assumption, I went ahead and I typed in accuracy of atmospheric pressure elevation in a Google search, and I came up with this post in Quora by this individual, Dick Lockwood, who's a staff geologist who looks like he's got a few years of experience under his belt. And here's somebody else who had the same question. If barometric pressure changes with weather, how can it still be accurate for altitude measurements? And he notes that the geologic fieldwork standard procedure is to have two recording barometers, one at a base station and the other taken at the location whose elevation is desired. Basically what he's saying is it's not good practice just to assume a static atmospheric pressure at sea level when calculating elevation. You actually need to know what the barometric pressure is at the time that you're actually taking your measurements, both at the place where you're taking your measurement as well as sea level, if you want to get an accurate elevation. And just to come around full circle, we're not doing that. We're not measuring pressure at sea level. We're just basically assuming a static number right here that gets forwarded to that function that calculates elevation. So that's why I'm getting this range in elevation for my calculated elevation where I'm taking my barometric pressure readings. So out of curiosity, I went ahead and I graphed the count of records for each one of those 5 deployments, or 5 real-time clocks. You can see that I had 2 RTC clocks that came in way low relative to the 3 other RTCs that were used with my data loggers. So something's going on here in regards to the number of records, and that's when I learned that these PFC real-time clocks can actually gain or lose time as a function of temperature. So my next question was to look at each one of these individually and see if the time recorded or reported by these real-time clocks is significantly different from the time that's being reported on my laptop. In order to test this, or to figure out exactly how far off the time on this little real-time clock was, I basically hooked this thing up to my computer and I had it echo the recorded time, and then I compared it to what the actual time was that was being reported by my computer. And this particular PFC 8523, I discovered accelerated time over a period of 7 weeks by about 8 minutes in a high temperature setting. And specifically, my check yielded a time of 8:45 with 12 seconds in the morning versus an actual time of 8:37:51 in the morning. So I went ahead and I did the same test for this second real-time clock that plotted way down on the count over here. So in this case, this one also accelerated time over 7 weeks by about 7 minutes in a high temperature setting. And here are the differences between the two. And again, I think this points to what I mentioned earlier in the video about the fact that this is a recognized issue with this particular RTC, in that temperature can have an impact on its time tracking qualities, and that can be fixed by modifying some of those parameters that are available in the RTC library for that particular chip. And then we've got these three chips that actually reported fairly close to one another. They weren't identical, but that they were fairly close. So that also made me wonder, how close are these to actual time? So let's look at this one first. And for this one, I'm actually going to have to wait to get the board back. It's actually on loan to ZeroCraft right now. The Pima Engineering Club is actually using this board to do some soil moisture monitoring experiments for my HOA. So when I get that board back and I plug it in, I'll post the results in the description of this video. What about this DS2231 chip? Let's see how it did. You can see that what's being reported by the chip is actually fairly close to reality, with the difference being less than a minute after 7 weeks operating in a high temperature environment. And here's the difference. Finally, how did this other PFC8523 perform relative to reality? These results are after 6 weeks, not 7. That's not a typo. The reason this one is 6 weeks is I actually had the foresight to think to check on the time on this before I loaned it to my friends over at the Pima Engineering Club for some experiments. Bottom line is that this one is actually closer to the other two PFC8523s in regards to time being accelerated over a long period of time in a high temperature environment. And here you can see the difference between the two. And here's the tabled summary for all 5 chips. And again, here's the results showing that the PFC8523 actually accelerated time by quite a bit over the course of 6 to 7 weeks in a high temperature environment. With these results in mind, I don't want to knock this chip. It's recognized that it will slow down or accelerate time as a function of ambient temperature, and that there are things that you can do to better calibrate its timekeeping properties. But frankly, I'd prefer to take Adafruit's advice and not hassle with all of that, and just purchase a DS2231 Precision RTC, which was really only off by a few seconds over the course of 7 weeks. If at all. So definitely this looks like a better option for me for timekeeping with Arduino data loggers. Alright, so I went over a lot in this video. This truly was a learning experience for me personally. So what are some of the lessons learned? First of all, when developing new sketches and tests, data loggers use SPI, and sensors and real-time clocks use I2C for communicating with the Arduino. And for data loggers to work, I need to have that chip select pin properly mapped. And in the code that I'll share and in also the example slides that I went over, you'll notice that I specified what the chip select pin should be for those particular combinations. The FeatherMO ADA logger, in my opinion, is a better option than the 32U4 ADA logger, only because it has 32K of memory versus 2K. And when you want to add things like additional sensors or OLED displays, you can bump up to that 2K memory limit on the 32U4 ADA logger pretty quick. And that's not as much of an issue with the MO ADA logger. And in my opinion, it would be really nice if all the loggers embedded an accurate real-time clock. The ADA loggers actually have that PFC8523 by default. And we already talked a little bit about some of the accuracy issues with those particular real-time clocks that need to be considered in code. It can be fixed, but it just takes a little bit more work. I would just like to have everything embedded in one package. A data logger with a good RTC functioning on a microcontroller that has plenty of memory. What about the results of the weather sensor test over 30 days? In my opinion, the DS3231 real-time clock is the best option for timekeeping when accuracy is a requirement. Looking at the results of all those different sensors, temperature and pressure readings were fairly consistent across all tested sensors, but humidity can vary, and I think that might be a function of sensor conditioning and also possibly the range that those sensors can actually capture, which needs to be better defined in the specification sheets. And also, accurate altitude requires real-time barometric pressure at sea level. To use a assumed constant just means that your calculated elevation is going to change over time. In my case, over the course of 30 days, I had a standard deviation of 20 meters, so that says a lot. So if I had to do all this all over again from scratch, and I had to pick a data logger and an RTC, that would give me the best, most user-friendly and accurate results, I'd definitely go with the Adafruit MO datalogger coupled with a DS2231 Precision RTC Featherwing. I think this is much better than going with the dataloggers that have that PFC 8523 real-time clock embedded in them, only because of those time accuracy issues. And I also appreciate the fact that the Adafruit Feather MO datalogger has more memory, so that I don't run into memory constraints when adding OLEDs or libraries for multiple sensors. If you consider the fact that you're also going to need an 8 gig SD card, you can buy a really nice data logger here for about $40, not including shipping. Not bad, really, considering that if you went with commercial options, you'd probably be paying thousands of dollars for basically the same functionality. Now, if money isn't an issue, I'd go ahead and recommend throwing in an assembled terminal block breakout and a Featherwing OLED into this setup. The terminal block breakout makes it really easy to wire sensors to your data logger. All you need is a little screwdriver and you can just wire them right into that terminal block. And then the Featherwing OLED is going to give you the means to actually see what your data logger is doing in the field via that nice clear OLED display. I've used these for field work for the Arizona Department of Environmental Quality. They're incredible, they're low power, they're just really nice little add-ons for any remote field deployment. If you throw in an 8 gig SD card, you're probably looking at about $70 for this bare bones setup, which should give you the ability to attach all kinds of sensors for your remote environmental monitoring and log data for months, if not years, on one of those SD cards, given how much memory comes on a standard SD camera card. As far as sensors are concerned, and in the context of what I tested, I'll let this table speak to whatever works for your own needs in regards to capabilities and performance. As always, I'll post all my code as well as the raw data files generated by the data loggers, as well as the Excel worksheets, including the pivot tables, to my website for your use and reference, pending additional comments and credit to Adafruit for authoring sensor libraries for Creative Commons use. Keep an eye on the description section of this video for further details, or just check back on modestmaker.com for updates. In my next video, I'll talk a little bit more about water harvesting and summarize an installation of an 870-gallon storage tank in my own backyard to capture runoff from my home and garage roof. If you like this video, please consider giving me a thumbs up. Thanks for watching, and I'll see you next time. So if all these tanks are equal, I'm guessing that's about 200 gallons so far. I don't see any leaks.